Hello everyone, in this video we are going to learn about reducible second order differential equations. So let us begin by considering the general form of a second order differential equation. A second order differential equation looks like a function of x, y, y dash, y double dash equal to 0. So this is how our second order differential equation looks like, where x is the independent variable, y is the dependent variable, y dash stands for the first order derivative of y with respect to x, and y double dash stands for the second order derivative of y with respect to x. Since it's a second order differential equation, it cannot have order beyond y double dash. It can certainly have a y dash term, and of course it can be involving the dependent variable and the independent variable. So that's how a general second order differential equation looks like. Now this differential equation is a reducible. By reducible we mean that we can reduce it to first order differential equation and adopt the approaches that we have learned from first order differential equations if either the dependent variable is missing. Here the dependent variable is y. Suppose y is missing, or the independent variable x is missing. In either situation, we can reduce this second order differential equation to first order differential equation and then solve it according to the method which is applicable as per the type which is involved. So a second order differential equation can be reduced, and it comes in this category of reducible second order differential equations if either the dependent variable is missing or the independent variable is missing from the equation. So let us learn the technique of solving such equations through certain examples. Let's look at the first example. Suppose we are expected to solve a differential equation which is a second order differential equation, say given by x y double dash equal to y dash. We can see that it's a second order differential equation where the dependent variable y is missing. There's no y appearing in this differential equation. So this certainly falls in the category of reducible second order differential equation, and the way we deal with such equations is quite elementary. We just introduce a notation, say p, for the first order derivative. If y dash is denoted by p, then obviously y double dash, which happens to be the derivative of y dash with respect to x, will be dp by dx. If p is the notation used for y dash, then y double dash is going to be dp by dx. And substituting this in the given differential equation, the equation can be rewritten as, in terms of p, the equation can be rewritten as x. For y double dash we have dp by dx now, and for y dash we have p. Now introducing this notation p for the first order derivative has made us land into a first order differential equation in p and x, and we know how to solve first order differential equations. We have learned a lot of types in the previous videos. So if we look at it carefully, then we can rewrite this equation as 1 by p dp is equal to 1 by x dx. It's the separable type. We integrate both the sides. So here we have log p, here we have log x. Since logs are involved, it's preferable to take log c here. And mind it, since it's a second order differential equation that we are solving, so in the answer we are going to have two arbitrary constants, because the number of arbitrary constants in the general solution of a differential equation is exactly equal to the order of the differential equation. So the first constant which appears in the process, I would prefer calling it as C1, because I know that there's some C2 waiting to come in to the solution in the end. So combining the logs, we can see that p is C1x. So that's the first level solution, because p was a notation that we had introduced. The original question was in y and x. So we just introduced the p notation to make it first order in p and x and solve it according to the technique which is applicable to get p in terms of x. Now once we have p in terms of x, p was a notation that we had introduced. We called y dash as p, where y dash obviously is dy by dx. So this implies that dy by dx is equal to c1x. Going back to the notational introduction, if we see p was the notation p was introduced by us for dy by dx. So replacing the value of p back by dy by dx, it becomes again a first order differential equation but now this time in y and x. Now again we see that it's a first order differential equation of separable type, which is very easy to solve. So we separate the variables. I can write it like this, and integrating both the sides I can get the solution very easily as y equal to c1 x square by 2 plus the other constant which I told you has to come because the order of the given differential equation is 2. So there have to be two constants in the end. So if I want, I can call c1 by 2 as a new constant. Let's say this implies y equal to, let's say, a x square plus b is the general solution. How does the general solution look like? It looks like a quadratic in x. Y equal to a quadratic in x looking like this is the general solution of the given equation. So when the second order differential equation is of a special type such that the dependent variable is missing, it is very easy to reduce it to first order differential equation in p and x. You call y dash as p and reduce it to first order in p and x, and once you get p in terms of x, then you put the value of p back as dy by dx. So it will be basically solving two first order questions. If it's a reducible second order differential equation, it amounts to solving two first order differential equations, once p in terms of x and then putting the value of p back as dy by dx, you get the final solution y in terms of x. Now let's see how do we do questions in which the independent variable x is missing. This was a sample which demonstrated how to deal with questions in which y is missing, the dependent variable is missing. Let me take one example in which the independent variable would be missing. The procedure would be somewhat similar with a slight change. Let's look at this question. Y double dash plus y dash square equal to 0, let's say. So we can see that it's a second order differential equation involving the dependent variable, the second order derivative, the first order derivative, and square of the first order derivative. So we can see that the independent variable x is missing here. Now when either x is missing or y is missing, we know that we can reduce it to first order differential equation, two first order equations. Step by step we'll be doing them. In the total solution we'll have two first order. So let's see, the technique is still the same. You call y dash as p once again. Now when you differentiate both the sides, because we need to have the value for y double dash, so what will happen? Our dp by dx will be y double dash. Now here you should note, in the earlier question where the dependent variable y was missing, we could straight away put y double dash as dp by dx. Now if we put dp by dx as y double dash in this question, we are going to introduce x. But since x is missing in the question, we do not want x to appear anywhere. So there will be one more step involved here. We'll be using chain rule to get rid of this x by rewriting dp by dx as dp by dy into dy by dx using chain rule. So this simple application of chain rule helps me to get rid of the dx term, because dy by dx is what is your p. So essentially you have written y double dash as p into dp by dy, so that there is no dx going into the equation, because x is missing. We want it to remain missing. Otherwise we'll have three variables in the system and we'll not be able to solve it. So let's see. When you do that, p is your y dash and y double dash has taken this value. So putting these two in the given equation, this value and this value, the given equation can be rewritten as, in terms of p and y, the given equation can be rewritten as, so let's see how does it look like, y into y double dash. So it's y into y double dash has taken the value p into dp by dy, plus y dash square is 0, but y dash is p, so that means plus p square is 0. So that's how the equation looks like in terms of p and y. Now you can see that p is common. If p is 0, that means dy by dx is 0. So that means y is equal to, you can see dy is equal to dx. Integrating both the sides, you can say y is equal to 0 times dx. So y is equal to constant. So these are the solutions which are trivial solutions. You can see that these obviously satisfy the differential equation. If I take y as a constant, then y dash is 0, y double dash is 0. So this is a trivial family, but it's an incomplete family because it's only involving one arbitrary constant. So this indicates that I've not got the complete solution, because in the general solution of a second order differential equation, there have to be two arbitrary constants. So this indeed is a set of solutions which falls in the trivial category. So I can assume P to be non-zero to get the complete general solution family. And if I assume P to be non-zero, I'll be able to cut it out here and write the given differential equation as y dp by dy plus p equal to 0, which again gives me an interesting type, which is the easiest type to deal with. It's a separable differential equation. I can integrate both the sides to write log p plus log y is log c1. This c1 is intentional because I know that there's some c2 also going to be coming in the solution. So combining the logs, I have py equal to c1. That's the first level crossed. We called dy by dx as p, and this second order differential equation reduced to a first order differential equation in p and y, but that's not the complete answer because p was something introduced by us. So let's go back to its value. P stood for dy by dx. So dy by dx, that means is c1 by y. Now once again you see that it's a separable differential equation in y and x. So I'll integrate it like this. Y dy is c1 dx. Integrate both the sides to get y square by 2 is c1x plus c2, or if I want, I can take this 2 to this side and write y square as ax plus b. That's my final general solution of the given differential equation. Now, so that means a second order differential equation can be reduced to a first order differential equation if either the dependent variable is missing or the independent variable is missing. If the dependent variable is missing, you just have to call y dash as p and your y double dash will be dp by dx. So this is the approach which helps you to reduce the second order differential equation into a first order differential equation in terms of p and x. And if the independent variable is missing, you start by calling y dash as p only, but for y double dash you have to, instead of writing it as dp by dx, you will write it as dp by dy into dy by dx, which makes it p into dp by dy. So if you do that, this substitution is going to help you reduce the first order differential equation into reduce the second order differential equation into a first order differential equation in terms of p and x or p and y, depending on the category that you are doing. Whether y is missing or x is missing, it's going to depend on that. And once you have p in terms of y or p in terms of x purely, then you call your you go back to your original notation. P was an introduction made by you. It stood for dy by dx. So you replace that value back, it becomes a first order equation again, and you solve it according to the procedure which is applicable. Whatever type it becomes, you solve it according to that type to get into the final answer. Please do remember that it's a second order differential equation, so there are going to be two arbitrary constants in the final solution of this differential equation. So that's all for reducible second order differential equation type. Thank you so much for watching.